Okay. Hello, everyone. Welcome to the eighth week of this problem solving sessions for your course. So before we start, so generally we start with the previous week's, quiz questions and all of that. Do you guys have any doubts in the lectures this time before we go to the quiz?
No, sir.
Okay. Anyone else? Fine. Okay, fine. We'll get started with the quiz then. Week 7 quiz. Um, okay. Okay, so for the first question that we have, um, what is the procedure that you have to follow? Anyone wants to take a guess? Uh, Let me know how you solved it.
Uh, I may I explain, sir?
Sure, sure, go ahead, please go ahead.
Okay. So first we need to find the pivot element. Where suppose
Okay,
we from right to left, we will find the string of I and string of I plus 1. If string of I is lesser than string of I plus 1, then that would be the pivot element. And after finding the pivot element, we will find the elements right side of those element, that pivot element, that right side smallest element which is greater than the pivot element, and then we will swap that. After swapping,
hmm,
we will reverse that all the suffix after I index where the
correct,
pivot belongs. That is the
correct,
final answer.
correct. That's exactly what it is, right? So in this case, let's say I have E, I, B, J, D, H, G, F, C, A. Um, it's not showing up here. Hmm. Okay, fine. There's some delay. Um, so here, as she was saying, that we need the pivot element. So pivot element is basically the from the leftmost. You want the you're looking for a non-increasing sequence, correct? Uh, that is your decreasing sequence. So in this case, because so C is greater than A, so you will continue the search. Okay, then F is also greater than C. G is also greater than F, H is greater than G. So when I say greater than, it's basically the idea that it is comes later in the alphabet structure, right? But D is not after H, right? So D becomes a pivot element in this case, right? And then the idea is you will find the largest element that is on the rightmost element, which is bigger than D. Okay, so in this case, your swapping element becomes F, right? This is your pivot, and this is your swap. Um, yeah, it's taking some time to take fine. So then after this, the next step is basically you will swap these elements. So you'll get F, H, G, D, C, A, right? This is your current subsequence that you finally get, I mean, that you get. And then you have to basically reverse it out, right? So reverse which part? Only the uh, reverse only the from the H onwards. This part you have to reverse, right? So this becomes then um, E, I, B, J, F. So A, C, D, G, H. Okay, that's your F, A, C, D, G, H. Yeah, right. This is your final this one, right? So finding the pivot element is first step. That is, you want to know where the non-decreasing, so not increasing sequence, starts from, and then you find the swap element, which is basically the rightmost element, which is greater than the pivot element. Then you swap them. That's the idea. And then remaining part of the code, you just a string, you just uh, reverse it. Okay, that gives you the next lexicographic, basically permutation. Okay, um, fine. This is quiz one. Our first question. Second question. Any thoughts? Any doubts on what the why the solution is the that way it is given here? Uh, what notes, Himanshu? I'm not sure. What are you asking? Current, yeah, there is some delay happening this time today on the web version. So, but it's currently showing up whatever is written on the screen. Yeah. So we need to reverse this. Okay. And again, as I mentioned, the recording will be provided. I mean, and whatever we are writing will be shared as a PDF. Okay. Fine. Which type of questions are asked in the exam? Again, I'm not sure, Imanshu. You'll have to ask on the discussion forum. Srinu, what is the doubt exactly? Which part is not clear? So in this lexicographic permutation, when you want, you first find the pivot element, which is basically the uh, element where the increasing nature of the reverse from backward, it stops, right? For example, here, uh, A is smaller than C is smaller than F is smaller than G and H, right? And similarly, but then H is not smaller than D, right? So you stop here. This becomes a pivot element. Then you find the swap element. That's basically the rightmost element, which is greater than D, right? So here G and H both are more than D. That is fine, but you want the rightmost element. So in this case, it will be F. Okay. Then you do the swapping first. So which is exactly what we get this string as, right? So F and D are swapped, and then you take whatever was the remaining part. That is this portion, same in length, whatever you have portion here, that you reverse it. Right? That gives you your next this one. So here permutation basically. So here the idea is when you say with alphabets, you just need to understand what value comes after the current value. So when you say decreasing sequence, it's about whether the element comes after the whatever value you have currently in the alphabet structure. That's it. Nothing else is that's all the idea here. Fine. Then your second question is basically we want to add a function called list max to the class node that implements the user defines list, right? So where list max computes the maximum value in a list where values are of type int. Fine. Incomplete thing is given here. Yeah. So now so we have three conditions: self dot value is equal to none, self dot next is equal to none, and return the else part, right? What does self dot value equal to none represent in this uh, custom list that we have? Anyone remembers?
Yeah, if list is empty, then it will reflect none value.
Correct. So self dot value being none means the list is empty, right? So if the list is empty, there is nothing to do max over. right? There is no max element present here. There's no element only. So how will you do max, right? So hence, the third option or the fourth option is a possible, thing that you can take. That is basically your none. So AAA will be in this case none. So this represents the list is empty. So therefore, okay. So therefore, A is none. Um, yeah. Then what you have is, okay, just a moment. Let me see if I can look at this working a bit better. Mm. Um, Final exam format, again, I'm not sure. Please ask on the discussion forum. Okay. Um, yeah. So in this case, as I said, so if self dot value is none, that means list is empty, right? As pointed out. The next condition is self dot next is none. What does this represent?
If tree is leaf, then it will reflect one value.
Sorry.
If tree is leaf node, means no next node is present over there, then it will be leaf node and it will return one value.
Correct. So it's basically saying that your list is having just one element in it. Correct. So it's a singleton list, right? So if it's a singleton list, the maximum value is just going to be that value itself, right? So hence BBB, the value that is mentioned here, right? So this has to be self dot value. Self dot value tells the value of the particular element, which is basically our, in this case, on this one, right? The value in the singleton list. Next condition is basically, so from these two conditions we know that okay, the value is not the list is not empty, and it has more than one element, right? So in that case, then we have two options: uh, max of self dot value and self dot next dot list max versus this other option, right? So what is the fourth option going to do? if if I, if you use the fourth option, that is max of uh, you know self dot value and self dot next dot value, right? What does this give us?
We will compare the current value with the remaining value.
Remaining how many? Remaining in the sense?
Remaining in the sense, we will compare the current value with the next one, left or right, left value or right value. Then after that, we will find the maximum and we will get the maximum value.
So again, remember, this is not trees we're talking about, right? It's a user-defined list. So there's no left and right. So here it is. So for the fourth option, what will happen is it'll just compare the current and the next value. That's it, right? But we want the max of the whole list, not just the first two elements, right? So this is going to give you the maximum of first two elements. Okay, so that is not what we want. So what we want is a maximum of the whole list. So hence what we do is we then instead of comparing with the next value, we um, basically compare max of self dot value and self dot next dot list max, right? So because list max is just basically going to give you the maximum element, right? From whatever is from the next pointer, that is whatever remains after the current node in the list, right? So whatever is the maximum, you compare that with the current value. That's it, because you want the maximum over the whole list, right? So this is the right option. Is this clear? Does this make sense? Um, So let's go over it once again. See, question 2, the first point is basically if self dot value is none, that basically means that the list is empty. If the list is empty, there is no there's nothing to do max over, correct? So hence your AAA, that is this condition, part of the condition is none, right? There is no element, so therefore none is the right option. Then when you say self dot next is none, that basically means that it's a singleton list, right? So there is no next pointer present. So hence, whatever the value is there currently, that becomes the maximum. So hence we use self dot value. Now we have two options. One is whether you do max of self dot value and self dot next dot value. So this gives you the current value, and this gives you the next value. That's it, right? So it's only the maximum of the current and the next. But what we want is we want the maximum over the whole list. So then we use a self dot next dot list max. That tells you the maximum value, whatever is there present from the next element, correct? So whatever is the maximum value, you compare that with the current value using this max function. That's the idea, right? This is the idea of recursion in this scenario. Okay, fine. Any doubts, please ask. Otherwise, we'll move to the next question. Okay, fine. Then what we have is this question, that is question 3. Jaswant, please mute yourself. Thanks. So next question is this foo function, right? So here what we have is we're saying that if self dot empty, you return 0. Self dot leaf, you return 1. Else you're returning whatever is there in the left subtree, same function. So self dot left dot foo will give you whatever this function returns for the left subtree, and then self dot right dot foo is basically the right subtree. Fine. Okay. Now, so here if you see again, this exactly sort of captures the idea, the feedback. See, it will not be the number of nodes because we are not counting in this recursion. We are not counting the current node itself in the first place, right? So it will never count the number of nodes because you're missing out on the current node computation, right? So it's only going to give you whatever is there in the left leaf, because that's the only thing that has a value called 1, right? So whenever we have a leaf node, you will get a value 1, right? And it'll keep on adding that value for the left subtree and the right subtree. Okay, so this will basically give you the number of leaves in the whole tree. Is that clear?
Yeah, clear.
So let's say if I had to do this largest value in this in the tree, how would you change the function? Any thoughts? If you have to find the largest value in the tree, then how will you change the foo function? What will you return so that when you do the recursion, you get the proper, uh, max value. Any thoughts?
So we are not getting your question. Can you explain it again, please?
So the current definition of the foo function gives you the number of leaves in the tree, correct? Now
Okay.
I want to, how can we modify this function, foo function, to get the second option, that is the largest value in the tree? How will you use this function, or let's say write a new function, that's okay, to get the largest value in the tree?
We will initialize a variable and count, that is, that counts the number of leaves. One by
Why you
one
want the
we will
number of
find the,
leaves?
we have to find the all the number of value in the tree na.
I'm sorry. You want to count the
Number of nodes in the tree.
number of nodes in the tree. Okay. With that, what you will do?
We will initialize a variable with count with 0,
Hmm.
and
Hmm.
we will increase the count by its leaf, return 1 1 1.
Hmm. That doesn't seem like it will work. So what you're saying is basically just keep counting the number of nodes in the tree, but that's not what we want, correct? Let's say if you want to write a function called tree max, which is there here on the right side, and you want the maximum value of the tree, right? How would you go about doing this? Uh, by adding dot max in the syntax. Where will you add dot max, Karan? So Anish, there's another live session tomorrow, same my session only, but there is no nothing 1 2 days before exam. That's the setting of NPTEL. We can find the max value in the left and right, and finally print the max from that. That's correct, exactly. How would you do that? So can you give me the code, Artika? Can you tell me how will you fill this? So basically, the idea is, as Artika mentioned, it's about finding the maximum in the left, maximum in the right, and then you just combine them again using max function. That's exactly what you want to do, right? In the final recursive call, left dot max dot foo. See, self dot left is again a tree, is again a node in the tree, right? What is node dot max? Remember, this is a bit, I mean, recursion with uh, class methods is a bit uh, uh, on the tougher side. When you say self dot left or self dot right, or for example, let's say when you were talking about the user defined list, right? When you say self dot next, that's again a node itself. That's again a node in the tree or the list, right? So it has to be a whatever operation you do on that, it has to be a valid operation. Here, the idea is that we are adding this function to the tree class itself. So hence, when I do self.left.foo, it's a valid operation, correct? Because self.left is again a tree, And for the tree class, we have defined a new function called foo. So this works, right? But self.left.max will not work because there is no method or member function, member value, which is defined by max. Correct. Maybe return max on this one. That's correct. Uh, and how would you go about doing that? Let's just go to the code here. So let's say you define something like this. Okay. So if self dot empty is one thing that we would have. Elif self dot is the, then you have else. So first, before we get to all the other paths, what will you do if self dot empty is true? What is the right thing to do? Anyone? Perfect. Right. So Akhil R is finally is done it completely. So it's self dot empty is basically uh, yeah. So you just return none, right? Because there are no elements present in the list, right? In the tree. So here you will say self dot value. Why? Because whatever you have obtained, that's a leaf node. So from that, there is no left or right subtree anymore. So the maximum value in that subtree, which is your just the leaf node, is the same value. So hence you'll do self dot value. And then what you'll have is you'll have max of. So now with this particular structure, you will get the max value. So here you will say self dot tree max, sorry, self dot right dot tree max, and then have another self dot left dot tree max, and then of course self dot value. Correct. So you'll compare the left subtree, right subtree, and self value also, right? That's the idea. Get the max of all of these. Right? Okay. Fine. Number of nodes, number of days is done. Yeah, length of longest path from root to leaf in the tree. How would we go about doing that? See, please mute yourself when you join the call. Okay. Jasmine. So longest path. How would you go about doing this? So again, let's try to use recursion as much as possible. It'll give you practice on how to do these things. Yeah, recursion, that is correct. But what would you go about? How would you find the longest path in the subtree? Yeah, that's the idea, right? So you want to take uh, uh, path in the left subtree, path in the right subtree, and then take the max of 2 and add 1. Why will you add 1? So self dot left dot, let's say longest path. Okay. And self dot right dot longest path. Okay. So this maximum will tell you what is the for count of the rows. That's exactly right. So the current subtree wherever you have that you need to also count the reaching to that particular point. Correct. So hence you will say you will have to add 1. So maximum, this tells you the what is the maximum length from that particular uh, root node to the left subtree, and the right subtree, and then the current one, right? So if it's empty, what will return? In this case, you can return 0, right? None is not required in this case because I mean longest path is also always going to be a number at the end of the day, right? So it's going to be 0, and here you can return 1. Correct? That's because that's your current what to say leaf itself, right? So the path is just 1, no other movement, just single current location itself. Okay, is that clear? So you can see basically the way we are writing the recursion, right? So here it was self.left.foo and self.right.foo. If you add a value called 1 inside, I mean, for this to this summation, you get the number of nodes. Here you get number of leaves. If you use the max function in this way, you will get the what do you call that, the largest value, right? So very powerful sort of a system to drive notations basically, right? And you can represent a complex problem in a simpler problem of the same kind, right? And then you try to merge the solutions that you have from the simpler problems, subproblems. Okay, fine. Okay. Um, okay. The last question for this quiz. Um, yeah. So in-order traversal of the binary tree has been different lectures. Then we have something called as a post-order traversal. So we discussed this post-order traversal last time, right? So where you first finish up the left subtree, then the right subtree, and then you process the root. Okay, that's the post-order traversal. So here in this case, we have a so let's just go with this one. Yeah. Yeah. So uh, so the post-order traversal is basically this. That is your EH, IC, BJ, FA, DG, and the uh, uh, in-order traversal is, so this is post-order. Yeah. In-order is EH, BIC, GJ, AFD. This is your in order. Okay, correct. So in order traversal, right? So now remember in the post order traversal here, as we mentioned, that you print the root at the last, right? For any subtree, right? So in this case, what will end up happening is with this definition, you know for a fact that your main root is going to be G, right? Because whatever is a last printed node in the post-order traversal, that becomes the root, right? By definition. So then you can actually construct the whole tree and say, okay, this is the root node. Now, in-order traversal gives you the idea of what is on the left subtree, left of the particular node, and what's the right, correct? Because remember, in order, you print the root in between your left subtree elements and the right subtree elements, right? So whatever is there on the left of the node, that will be your values present in the left subtree, and vice versa, right? So that you can verify here. So now this becomes your left of G, right? So EHBIC, the first 5 elements in order traversal, that becomes your left subtree of G, right? And the right subtree will basically be J, A, F, and D. Okay. So then what you can do, what's the question though? Um, left child of the root node. Fine. So then now with EHBIC, so we know that EHBIC is one complete one subtree, right? Left subtree of the root node. So then we can look at that particular elements, all those elements ka post order traversal. So that you can see it here. So EHBIC ka post order traversal is here, right? It's EHICB. So again, remember post order, you print the root in the last. So hence B becomes your uh, yeah, so this is a new, what you can say, the left node basically of the root. Okay, so this becomes your new tree. I mean, this becomes a B. Fine. So the question ends here. Then, so therefore, B is your answer, right? And then you can keep on continuing this whole process. So you can actually construct the whole tree from just the post order and in order traversal if you have it. Okay. So in this case, let's just see how to do that. You have the remaining part, that is JFD. Now you can see JFD in the post order traversal. So here D is the last there also. Yeah, D is last there also. So therefore D becomes the root of this right subtree. Okay. So this part becomes your right subtree. So then you again continue. So now with this, what we'll start is we'll start the next session. That is your EH becomes a part of the left subtree of B, and I and C become the part of the right subtree of B. Okay. So again, so the idea is you keep on going between post order, in order, post order, in order. Post order tells you the root, right? And in order tells you what split you should make in the nodes. Okay. So let's just do that. Yeah. So EH is left part of the B. And in that, when you see EH in the post order, H is towards the end. So that becomes the root, right? So that becomes the node here. And then you have E has to be on the left part of H. So that becomes your, okay. So this completes this. Then I and C, when I look at it, C is again later. So C becomes the root here. And then I is to the left of C. This becomes a left subtree. It's taking time to update. Okay. So yeah. So can you does did this part make sense to you? So see, we have taken G as a main root, and then the left part, all these nodes are supposed to be on the left side of G, in the left subtree of G, right? Because of the fact that you get the information from the in-order traversal. Okay. Then in that, again, you can look at the post order for these nodes. So in this case, we got the B as the last node in the post order traversal of these 5 nodes only, right? So that gives us the root of that subtree, which is B. Okay. And then you can do the same thing here. So then again, you look at the inner traversal and then split based upon the B here, right? So you have EH and IC. So EH has to be on the left subtree of B, I and C have to be on the right subtree. Then again, you continue. For EH, what is the root node? So root node will come from again the post order traversal. So again, E and H is on the right side, so that becomes the root, and E becomes the left child of H. Same thing, you continue here. I and C have to be on the right side of B, but in that C has to be the root because of the post order traversal of these two, right? So this becomes the root, and I has to be on the left side of C, left subtree, because it follows, it's before C in the in order traversal. Okay, is this clear? Okay. and then we can go ahead and complete the remaining part. So I'll just do that quickly. So here D becomes the the root, and then we see that J, A, and F are all on the right side, on the left side. So there's no right child of D. There's only left child. So then in that again JFA is the postorder traversal. So A becomes the root now, right? And A becomes the root. Left side you have J, right side you have F. So left side J and right side you have F. Okay. Yeah, just a moment. Okay, fine. So hopefully it made sense. So same thing you can do when you have the pre-order traversal. Okay. So remember, it either you want the pre-order or the post-order, right? So pre-order plus in order, you can construct the whole tree. Okay. Or post-order plus in order. So because the idea is both this pre-order and post-order will tell you exactly what is the root of that subtree, whichever you get, correct? Because in pre-order, again, remember, we print the root first, then the left subtree, and then the right subtree. So in the post-order, we looked at the last element. In pre-order, you'll take the first element because in pre-order, you print the root first, okay? With that, once you have the root of the subtree, you will now use the in-order traversal to understand what elements should be in the left subtree, what elements should be in the right subtree. Fine. And just giving you, just having pre-order and post-order, just these two alone by themselves is not enough to construct the tree, right? Generally not enough. Okay, so pre-order plus post-order, let's say, this is not enough to construct the tree completely. Okay, you will have some ambiguity in it. So the simplest example could be something like, let's say, A and B. Okay, so let it load. So let's say you have A in the root and B is a child of it, right? There are only two nodes in the tree. So then what will happen is you will end up having the pre-order will be AB, correct? First your root, then the node is your pre-order, and post will be basically left, right. Then you'll print B first, and then you'll print A, right? But in this case, let's say if you have A and B like this, yeah, this will also have the pre-order being AB, and post order will be BA. Simplest example. Okay, so AB present like this will have these pre-order and post orders. Let it come up. Yeah. So as you can see, so if I have two very simple trees, A, B like this, the pre-order traversal for this tree is going to be A comma B, right? Because first you print the root, then the left and right subtree. In post order, it's going to be left subtree, right subtree, which is B, and then the root, BA. Okay. Same thing for this tree also, right? Root and then left, that's your pre, and then left, and then the root becomes your post order, right? So both have the same pre and post order, but the trees are different, right? So hence, just using pre and post order, you cannot get the tree structure, right? Okay, so this completes the quiz. Uh, any doubts? Please let me know. Now let's put So how many of you have gone through the lecture videos for this week 8? So what is memoization? When we are looking at let's say a Fibonacci sequence, uh, because that's exactly where it becomes useful.
Storing in the table the previously searched value, previously answers, so that you can use them without calculating again and again.
That's exactly correct, right? So what we're doing here is we're just trying to store the previously computed values so that we don't have to recompute them. Okay. Uh, yeah. Okay. So let's look at a simpler. So this is your table for your Fibonacci sequence when you're doing it using memoization. So of let's say 5, right? So so what you're doing here is you're maintaining a dictionary, right? Using this fib table underscore memo, right? So what it does is basically if there is a okay, by the way, what does this if condition tell you? If n in fib table memo, what does this mean? What is this checking? If n in fib table memo, fib table memo is not a list, no? Then what is this n in this one? What does it mean?
It is a pair, key value pair.
It's a key value pair, correct. So what we're doing, as Karan said, it's basically we're checking whether the fib table memo has a key named n, right? In dictionary, when you're doing this sort of a operation, it is not searching in the values; it's searching in the key. Okay. So what we're saying here is that key n exists, right? So basically, I mean, there's a value against key n, right? So if it is present, you end up just using that. If not, you then compute. And after computing, obviously, you need to store the value again, right? So the storing part happens here, right? And the computing part is very straightforward. It's just basically calls a recursive call, right? Fine. So 4 is also enough to do that. 3 and 2. Okay. So but in this case, again, remember, you need the whatever table you have, that is in our case dictionary, that has to be basically global in nature, right? Because each and every recursive call should be able to write to that particular dictionary, okay, that table, right? So here again, fib memo of 4. So 4 is not present initially, so we're just calling fib memo of 3 and 2, correct? Again, see, we are in the recursive call. So we have called with 3. 3 also we don't have a value. 2 also we don't have a value. And for 1 and 0, we know it's going to be the value is 0 and 1 respectively, right? So yeah, so fib memo of 1 is going to be 1, and that has been stored in the fib table memo, right? So that you can see here, right? So we have stored 1 against 1 here, all right? So then we come back here, we say again of 0. So 0 also we stored it back. again, see this dictionary here. That's your, so we have stored 1 against 1, 0 against 0. And then is where we have the, yeah, so again, for 2 also, we're storing it back, right? So so all of these things are new for the table, for this function. So hence there is no use of the table yet, the function yet. Now we come to this condition. So where we are saying that if n is in this, so that basically n is 1, then for that 1, we have already done the work already. So we use that value from the fib table, right? That gets used up here. So n is equal to 3. We have again written that value in the fib table. So just look at the table here, right? So we have 2 stored against the index, so that is 3, right? And then for 2, so 2 would have branched out into fib of 1, fib of 0 in usual recursion. Here, because we're storing the values, so now with 2, we already know what the value against 2 should be. So we use that to fasten our work, right? So now the last operation is basically 4, which is exactly what we want, right? So hence we get that final value, that is 3. Okay, so very simple idea. So the point is you just need to store whatever values you have computed previously in the inner table. Okay. Similarly, so what is the difference between dynamic programming and memoization? So here also we are going to store in a table and format and all of that, right? So we are doing that here also, right? In the memoization step method. So then why do DP? Why not do this memoization? Any thoughts, anyone? Iteration. That's exactly the point, correct? So even though we are storing in the table, right? We are still doing recursion, correct? So hence we end up doing that work of stopping the process and then starting the function all the way new. Here we are doing it in a much simpler manner, which is like a for loop, right? So that is then used in this scenario. Okay. And so, but in DP again, I mean, in both of them, DP or in recursion, you need to know exactly in what order you will go and fill up, right? That ordering you need to be clear beforehand, otherwise it will be difficult. Okay, so let's look at that. Yeah, so fib table initially is 0, I mean empty. So for 0 and for 1, it's straightforward. We just add in the values, and then now we'll start the loop, right? So from 2. For 2, it's going to be 1, the value against 1 and value against 0, right? And you keep on filling up the table in this format. And finally, what you want is the fib table, table of 4. That's exactly what our output input was. So we ask for that particular final output, right? That's your C. Okay. Is this idea clear in DP versus memoization? Any doubts? Okay, fine. So then we'll go to the grid paths example. So does anyone remember grid paths? What was the problem statement? What do we want to find in this grid paths problem?
Sir, one thing, could you please explain again DP versus this one, memoization?
Yes. So in both of them, at the end we have to store something in the dictionary. That is something that cannot be. Hello. Yeah. So Yeah, so basically the point is in both of them we have to store something in the dictionary or by definition, right? Because you don't want to repeat the work that you have done previously. But the idea here is in memoization you still do recursion, right? So see, you can see here that we have the function calling the same function with a different argument, correct? So this process is basically sort of like a with adding some extra stuff to the recursion itself, right? So but recursion itself is a bit more costly than iteration. Okay, so where you need to suspend a process and then compute the called function, then come back and resume the previous function call and all of that, right? So that part is also removed by DP, right? So in DP, you try to find an iterative solution to these problems where sub-problems are basically repeated, right? So hence you want to store the solution somewhere and then reuse it. That's the idea. Okay. So you see, also remember these are useful only when you have this when you have the same subproblem being repeated somewhere. Okay. For example, let's say if you wanted to find something like a sum of lists, sum of the elements of a list. Okay. So where uh, using a recursion, right? So let's say sum list is, let's say, L. Okay. And what I will do is I'll say if length of list equal to 1. There's only one element, so it's going to be return L of 0. Actually, then you can just do length of list equal to 0, return 0, right? And then else you will say return, let's say L of 0 plus sum of L1 colon, right? So what this tells you, it tells you to find the sum of the elements of a list in a recursive form, right? But again, remember here there is no in the whole process of writing this solution, there is no sub problem which was repeated while solving this problem, right? So hence there is no need of storing the whatever you have gotten the output as. Okay, that is the idea. Only when you have repeated subproblems being used somewhere in the or the other to solve the final problem, then the storing will help. Okay. Okay. Hopefully this was clear. Um, yeah. So grid paths, yes, somebody told. Yeah, going from one point to the other. So no, but uh, so what? Yeah, it's a possible number of ways, right? So how many possible ways are there? How many? So you want a number in the integer, that is basically how many possible ways are there to reach from 0 0 to whatever point you want to go. And there's a constraint. The constraint is basically you can either go either towards the right or towards the top, right? I mean, assuming the point that you want to go is lies in the first quadrant. So that's the idea, right? So you want to go from 0 0 to the point in the quadrant. Okay. Uh, Now in this, very simply, so this function that you have is the simplest function that we have in terms of the recursive call, right? So let's say you want to go to some destination. Again, remember, so a holes list is basically, let's say if there is a hole on that particular location wherever you want to go, correct? So then obviously there is no path that can lead you there because that particular place is itself not existing anymore, correct? So hence this condition tells you that if whatever destination you want to reach to, that is that is a quote unquote hole, then you cannot go there, right? So there are no paths reaching from 0 0 to that particular location, right? And then you are trying to look at so now we have the xy coordinates basically I and j for the destination. If I is 0, j is 0, so just one single path, that is a self loop basically, right? So from 0 0 to 0 0 is just one element, one path. Then let's say on when I is 0, this basically tells you the uh, When I is 0, that's basically your column, correct? Your y-axis sort of, right? So in y-axis, then you will just say how many ever paths were present to reach j minus 1. That you just need to same path will be present to go to that particular location, correct? That is your uh, I equal to 0 condition. Same thing with j equal to 0 condition. So this is your x-axis, correct? Now what you will say is you will say, okay, so now I would want, to reach a particular destination, I can either go from left of the element or below the location, right? So this basically tells you the left of the element. So same location but left, and same location but bottom. Okay, so this is your usual function, right? But now, as you can see here, that you will end up having some sort of repeat computations, right? Uh, so there's a possibility that these values that you have I minus 1 comma j or I comma j minus 1, you might have computed them beforehand somewhere in the process. So hence what we do is we use either the memoization or DP approach. So in the memoization approach, again, remember, we need to store it as a table in some way, right? So here I'm using a dictionary. Uh, yeah. So, and that dictionary, I will have basically the destination itself as the key. Remember, we are representing destination as a tuple of I and j. Okay, and tuples can be keys in a dictionary. So hence we are using that, right? So if so this is the part where we are reusing already made computation, right? Already computed value, right? So we have the dictionary here, and if we already have a value that should be present that was computed, we just reuse that. Otherwise, you do the whole process neatly here. Okay, fine. So again, same idea. So if it's a whole, then the value is 0. If it's the origin itself, then it's 1. Otherwise, the respective uh, column, respective row, I mean the first row, first column, and then otherwise you just call this function again, right, for the left neighbor or the bottom neighbor. That's it, right? And store it again. That's the main point. Whatever value you get, you store it against in the dictionary and then return the value back. Does that clear? Your any questions, any doubts on this? No? Okay. And then we have the DP version, right? So again, remember in the DP version, so again, we need a dictionary, that is correct. And in that, what we're going is we're doing it, at least in this case, we're going row by row, right? That is column by column. That's basically your first x equal to 0, then x equal to 1, then x equal to 2, and that way. That is this loop, right? So where you go from I and j for the destination I until destination j, right? And then you're checking again, exactly same process here, right? So you're saying that, okay, if it is, in the whole list, so that value has to be 0. Origin is again just 1, but the first column, first row, same conditions, and this is your final saving part, correct? So where you so basically here again, remember, this is not a recursive call. It is just using whatever is present in the dictionary, right? So hence when you're doing the DP, make sure whatever subproblems are required to solve the current problem, they are computed before. And that's exactly why you need to know the path in which you will compute your solution, right? So here you're going from the origin all the way, every column, all the way until the last column. Okay, that is the idea. And in that also, you're going from bottom row to the top row. Okay, so hence you will have, so this will make sure that that makes sure that procedure will make sure that you have a valid value present when you're trying to solve this this part of the problem. Okay, is that clear? So then you can, let's just see. Yeah, so here, for example, let's say you have two holes in the process. So 2, 4 and 4, 4. Same problem, same we are taking as present in the lectures, by the way. So let's just see the solutions, right? So here, first one is basically your simple recursion call, right? So this, it will recompute whatever you want, right? So that tells us that there are 1358 ways to go from 0 to the 5, 10 location. And here I'm printing the whole dictionary itself, but yeah, let's just see. So DP solution again, this will tell you the whole dictionary, and you can look at the last location, right? 5, 10. So this tells you the number of ways to reach 5, 10 from 0, 0. Okay, which matches the recursive call. Okay, same thing with the memo function, the memoized version also, right? This also has 1358. Fine. Is this clear? Okay, so here, see, so we are storing it as a dictionary with a tuple as a key, but you could also store it as a two arrays, two lists, sorry, right? List inside a list, right? And then basically keep on updating the values in that list. Okay. Now, the main use one major difference that comes between memoization and DP is basically this idea that uh, memoization will only solve those subproblems which are useful for solving the current problem. That's it, right? So this particular example, this holds list, is basically that scenario, right? So where we had that condition where the top uh, uh, the second top row and the second last column were completely filled with holes, right? So hence uh, there is no way to reach. Yeah, so there is no use of understanding the number of paths to be computed to reach these nodes, because we know for a fact that this whole region is now useless, right? To reach the destination, that is your 5, 10 in this case, right? So that you can see now. So this is your host list, for example. If you do, let's say your DP versus this uh, method, right? So here you can see in the first dictionary, you can see like almost every value has gotten its entry, right? And the dictionary for the memoization approach ends here itself, right? Whereas here, all possible values have a entry in this particular scenario, right? And the value finally is 2, which is the right number, but it has computed so many intermediate values which are not useful. For example, let's say 3, 8, right? 3, 7, all of these, there's no way to reach from there to the destination. But whereas in this approach of memoization, we have just computed very limited number of values. Okay, so you can just see also how many values we have computed. Let's just say length of full text and length of class memo. Yeah, so this is done 66 and this is done 42. Okay, but again, remember, as professor was saying on the video, that even though this can happen sometimes between DP and memoization, but prefer DP in general. Okay, that's the idea. Is that clear? Any doubts? No? Okay. Yeah, so then we have the longest common word and longest common subsequence. Um, so we'll use the same example as was present in the lecture, right? Bisect and secret, right? So longest common word in this case will be S, E, and C, right? Because it has to be contiguous letters, right? In both the strings, that is A and B, right? Whereas longest common subsequence is going to be S, E, C, T, right? Because here I can drop R and E and get this matching number of matching subsequence, right? In both of them. So yeah, so what's the main logic in this longest common word idea? Anyone remembers? I put it on the screen with a highlight. For longest common word, what is the main logic idea here? People who have gone through the videos. So here the idea is that we are saying that if, let's say, any point between the the whole matrix, right? So where, let's say, each possible combination we are looking at. So in case wherever they match for the first time, right? So then we'll say that whatever is there for the next set of values for next um, um, character, right? In both the strings, you use that and you add one to it. That's the main idea here. Okay, and remember again here we are going from yeah a the to you're going from towards the end to from the end towards the start. Okay, that is the idea. So we're going from C R. They go from the end of the first string and the end of the second string, and then you go towards the beginning of the string. Okay, is that clear? Any doubts in this? I mean, it's a simpler. I mean, it's a similar code as the this one. We can run through it if you want, but okay. So for this, what we do is again we want to create a table. So we'll do that here as a dictionary in which keys are tuples, right? And what we're doing here is we are creating the table with zeros in the last column and the last row, correct? So where is the yeah. Yeah, right. So here we are storing the X and Y, that is R and C basically, and we are basically giving the last entry to be zeros, right? That becomes your this part of the code. Okay, that's basically your for R in range of length of U and all of that. So this makes sure that the edges basically are zeros, right? Left and bottom edge, right and bottom edge, sorry, right? And then what we do is we are saying where in case wherever they match, you just add that one particular element that is the current match plus whatever has matched in the previous iterations. Okay, so let's just see how that works. Yeah. So in this case, we are saying U of R and V of C, correct? So T and T, that's basically right. So because they both end with T, So the T and T, that is what is happening if we had the first match with, and then we're saying you add one with whatever is in the future, in the next part of the string. So that is in this case going to be 0, right? Because we know that the string ends actually at T, so the next part is just going to be 0, right? We do that, and then we see a lot of values which are zeros because they're not matching at all, correct? So in this case, for example, we're looking at U of R and P of C, right? So we're going from your this A string and the B string. So one by one, we look at all possible combinations, right? So it's going to be a table with all possible values. It's your n square sort of a table, right? And let's just go to the interesting cases. Yeah. So in this case, it's going to be R and C's 3 and 4, correct? So U and B, right? So here we are, I think we're matching the C, I guess. Oh, E, yeah. So E is being matched, correct? So this E and this E matches, correct? So we then say, go ahead and increment with the previous value. Again, that is going to be in this case 0, right? So R plus 1 and C plus 1. That is in this case, we have C, that is this for C and this T, correct? So for U of, in this case C and in this case T, they are anyway not matching. So that value was 0. So we're just saying add 1 to that value, correct? And then you keep on doing that. Here now we have U of R to be C, okay, and B of C to be also C, of course. And then you have this 0. So we're now looking at this C and this C, right? Because you can have CT and then CT here, right? That's possible. So hence we look at all possible combinations and keep updating it, right? So let's just look at that. Yeah, so U of R, okay, then 3, that becomes yours E, and then you get this. So you get now U of R is S. So we have come to the beginning. So where we know that SEC is going to be the value. So we just look at that. So we know for a fact that the next portions of both the strings, correct? Next portions of both the strings, they are matching and that length is 2. So now even this is matching. So I'll just add 1 to that length, that is, and becomes 3 basically. So we then get, so which position basically which is a position which has a max value in it, that's basically 2, 0 in this case, right? So that's telling you that for the first string, it's starting from the index 2, this third position, and 0 index in the second string, that is your B. So you have S, E, and C from here and here. Okay, this is the longest common word. And then we have this longest common. Okay, any doubts here? Any questions? Right. So then we come to the longest common subsequence. So in this case, the idea is that we want the we can let go. So we can let go of some characters in between, correct? So that basically makes the problem a bit complex, but again the construction is very similar, right? So again we're just going to start with all zeros on the right column and the bottom row, correct? And then whenever it matches, again the idea is similar, right? So you just say you increment 1 to whatever the count was present till now, right? If it doesn't match, we're going to take the maximum of whatever is possible, right? Again, here we can take two possibilities. Either you increment the first string or you increment the second string. So this is the first string increment, right? So basically you look at the longest common subsequence from the first string ka next character to all the characters in the second string, or the current character in the first string and the next character in the second string. Okay, this max function helps you to identify that. Okay, so let's just look at the chart. Yeah, so first condition we have gotten is this basically is the T condition, T letter, right? Secret and bisect T, right? So that becomes your first idea. And now here again, we're going to look at yeah, so in this case, it's going to be zeros and all of that, but yeah. So we are saying, so we have now moved on to yeah, R is 4 and C is 5, right? That's your fourth index here, index 4 here and 5 index here, right? So we're saying that the longest common subsequence from this particular part of the string to this string, right? That's what we're trying to ascertain. And in that we're saying you either increment this and compare, or you increment this, and this has no to the string is ended, right? So hence the value is 0. That is this particular value, right? That's 0. And this is 1 because we know that the next string, that is your T and T match. Okay, so that becomes your LCSS of this particular value. Okay, so let's see when we reach I. Stop that. Yeah, so we have now come to the condition where where the I string, sorry, I character, right, in the bisect. Fine. So let's just see how this is functioning now. U of R is equal to V of C. Ah, yeah, we can change the code on live. Fine. So then we are at the I location. So for when the character is I basically, then nothing is matching. So we'll look at the next parts of it. Correct. So bisect. So we're looking at SECT, right? With, let's say, what is V of C in this case? We're looking at T. Yeah, just a simple the last character, right? So we're looking at SECT with T. What is the longest common sequence versus, let's say, with the value incremented for the second string, right? Which is again going to be 0 in this case, right? So that gives you, for the first one, it'll give you 1 because only T matches until now, and the second value is going to be 0, right? So you keep on getting for every possible, possible pair, what is the longest common subsequence from that particular index to the last index in the first string and the second string, and keep on adding 1 only if you find a proper match. Okay, that's the idea. Again, you can get the max location and all of that, right? This is the longest common subsequence. Any doubts here? Yeah, so assignment 6 we did last class, and the videos are uploaded, so you can just look at the video, recorded video. Any doubts in longest common subsequence or longest common word? No? Okay. So last example in this idea of storing computations and stuff like that and finding the optimal one. So here we are dealing with the matrix multiplication, multiple matrix multiplications, right? So where and we want the parenthesis. We also want to know which is the final solution that we got, right? So again here, um, so slightly bit different from what is present in the code in the sorry. Yeah. Huh. So slightly bit different from what was present in the classes, right? Um, so what we want is, let's say we want to multiply matrices, which are three matrices, which have these dimensions. So it's 10 cross 30, then 30 cross 5, and then 5 cross 60, correct? So in this, the idea is that we are looking at all possible, pairs. Uh, so you want to find the optimal split, right? So where should parentheses so that you can have faster computation, right? With least number of computations, correct? So here n is the number of matrices becomes, right, because here we're saying that we we are giving the dimensions from the first matrix dimension to the last matrix dimension, okay? And because they have to commute, sorry, because they have to be valid for matrix multiplication. The second the first matrix's number of columns has to match the second matrix number of rows, right? So hence we have just given that once here, 30, right? Okay, in this way. And then so what we have here is basically the what is the amount of computation it will take, right? And what is the split that we want, correct? I mean, what we got, the best split, right? In this case, then this is basically you're going from all possible matrices in this case, right? Um, and then you're looking at in the remaining number of matrices uh, for the subsequence from I to J, correct? I less than j, basically, right? I to less than j. What is the number of computations that you would get for to get optimally, right? So then you look at all possible values between I and j, and you then see what is the value present for I to k, right? If you were to multiply from I to k the matrices, then k plus 1 to j matrices, right? So that is the values that you have already present in this DP list, right? And the current matrix, that is whatever you got finally after multiplying those two matrices, you have to multiply these two matrices again, right? So that basically gives you the this gives you the number of operations to do for this particular multiplication. And then you're looking at which is the optimal one among all possible k. So this is that loop where you keep on updating the value for dp of I comma j, right? So whichever you find as optimal, you will keep that, right? And which split, that is what we're keeping it here, right? Because you want to know exactly where you did the matrix multiplication, right? Yeah. Okay. And then yeah, so just building the parentheses in this way so that we can see visualize what is coming out of this, right? So in this case, for example, we have 4,500 operations which are going to come from this particular optimal way of doing it, and the grouping basically is going to be A1 A2 first, right? So this is the A1 10 comma 30, then A2 you multiply, that is 30 comma 5, right? So this gives you, so 10 into 30, 10 into 30, right, into 5. This gives you the A1, A2 multiplication, the number of compositions to happen, right? Then plus you would have whatever is the final, size of A1, A2. So A1, A2 size will be 10, 5, right? So then you will have 10 into 5 into 60, which is your resultant of A1, A2 with A3, right? This will give you your 1500 plus your 3000, okay, which becomes your 4500. Is this clear? Similarly, you can do for the remaining ones. And in this case, for example, it's A2, A3 first. So these two matrices, this A1, this is A2, A3, this one first. Then you multiply with A1, this matrix, and then finally with A4, right? And again, complex versions of this, you can try for a lot of different things here. So you can see A1, A2, A3, A4, A5, A6, and then the resultant here, and then final resultant. Okay, fine. Any doubts in this matrix multiplication? So before we, uh, you know, close today, so tomorrow also there is a session. Uh, um, Same timing, 6 to 8. So what shall we cover in that? Any concept or topic that you find difficult, you want a revision of? We can do that tomorrow before the exam. That will be the last session that I will be taking. So in the all the 8 weeks courses that we have, right? So any specific topic that you want me to cover, uh, we can do that. So if you let me know, I can prepare accordingly, and then we can, make it a more useful discussion than just. Or you want like a rundown of the whole thing, for example. Any concept you find difficult, by the way, or is everything easy? Rundown. I don't know what concepts are important for the exam. Again, exam pattern is not in my hand. Okay. So we can start today itself for that, for example, rundown. We have some time left. Um, in basics of Python, for example, we have the different types of, you know, uh, variable types, right? We had int, float, bool is mentioned here, strings, lists, and all of that. So this is something that we yeah. So let's say you have a list. We can do this, I guess. Let's say I have a list 0 into 4, right? Okay, so by the way, what does this do? This statement, what will L be if I do something like this? L is list of 0 into 4. What does it mean? Anyone? What will print of L give you? What you either you don't know or you're not telling. This one, the first option is more scary. 0 in 4 lines. It'll print 0 4 times. That's correct, right? So it's basically a list with having 4 elements, which each of them are 0. Correct? If I now, let's say, if I were to define something like this, what will this be? What is L2 now? Five times L, right? So L is basically your 0 4 times, 0 4 times. So hence you have a list like this, right? It's a list of lists. Yeah. If I do now something like this, list of L2 of uh, 2 of 3 equals to 4, right? What will be L2 in this case? Anyone? Zero zero four zero. See, I'm doing for L2, huh, by the way, not L. L2 of 2 of 3. Three people told 0040. Okay. It's L2 of 2 of 3. So it's basically L2 of 2 means the third list, correct? And there are 5 lists in L2. That much we know, right? So there are 5 lists. Third list ka fourth element. Okay, that is set to 4 in this case. Okay. Is this correct? I thought we're just setting the second list ka third element. No, it seems happening in the first list also, second list also. Why would this be happening? Anyone remember what lists in Python do? I mean, how many remember mutable, immutable? Correct. So, correct. So Karan is right. So basically here L2, yeah. So L2 you have 5 times L, but L is that pointer. It's the is a memory location of this list. right? So when we are saying L2 of 2, it's actually the same list in L2 of 0 or L2 of 1 and so on and so forth, right? And that list's third element, which is the last one, right? Last element gets filled as 4, right? Now, because the first and second and all the lists in L2 are actually pointing towards the same list, so they end up giving you this sort of a representation, right? So though you intend your let's say your what you wanted to do was to just update the second list and its third element to 4. It's ending. It has updated all the elements, all the lists, the third fourth element, right? Uh, so how do I fix this mistake then? Let's say I want, you know, 5 lists, okay, inside a list, right? And the the third list, ka fourth element should be 4. Nothing else should be 4. Remaining everything should be 0. How do I do that then? Any thoughts? How should I construct my list? Let's say L3 is a list, okay, um, such that it should have, it's a list of 5 lists, 5 lists in it, right? Each list is 4 elements, right? Everything 0, except third list's fourth element, which should be 4. How do I do this? Create a sublist by slicing and updating it. Okay, tell me how you will do that. Give me the final code. Come on, now, to matlab, you're studying Python for 8 weeks. So now you shouldn't even talk in English. You just talk in code. So how do I make sure this happens in my list L3? Copy to another list and change it there. How? What is the code? What you will write for it to happen? So where is the main issue coming in? The main issue is basically we are getting this sort of, this multiple copies of the same list, right? So how do I end up, how do I try to solve that? Will something like this work? Convert L3, L2 into a list. Matlab? Ravi Suryadevara. So you have said L3 is equal to L2, L3 of 2 of 3 is equal to 4. No, but that still won't work, right? I mean, let's say this is you, this is if I do that. L3 is equal to L2. If I do this, is again still pointing to the same list. It's become even, L3 is now also pointing to L2, which is a list of same list again, right? So this won't work. Anybody else? Copy dot deep copy. Okay. So you'll copy dot deep copy what? L2 is it before I assign? So let's say if I do something like this, let's say L3 is equal to L into 5. Okay. Now let's just make another one. SL is equal to 0 into 4. Right. And now you're saying to deep copy what? Who said that? Akhil? Yeah. So what do I deep copy? What are you saying to deep copy this one? What if I do something like this? What about this? Will this work? Any thoughts? So this is also not working because again the idea is similar, right? Zero element list into 4 creates one list. That list element, that location pointer is copied 5 times. Is copied 5 times in this, right? So hence this also won't work. Any other approach anyone has? What about list comprehensions? Can we use list comprehensions somewhere? Okay. So one possibility someone has said is L3 is equal to L2 2 colon. Okay. Then L3 of 0 3 is equal to 4. Print what? L3. Ah, so again, same issue, right? See, L2 of 2 colon, I understood what you're trying to do, but again, remember 2 colon is, I mean, 2 colon is going to give you from the third list, which is fine. But again, the internally, the element in that list is again a pointer to to this L, which we had. So you manipulate anything in that, it's going to manipulate the whole list, all copies. Correct? So anyone on the lines of what to say, list comprehensions? Let's say for underscore in range of 5. Okay. Score in range of 4, I guess. Yeah. All right. Let's just see if L of L3 is correct or not in the first place. Yeah. Right. So I have 5 lists. Each list is a 4 element list. Right. Let's see if this one works. This works. Right. Because see what you're doing here is you're doing like a for loop inside, right? Inside it, right? So whenever this range of 5 that is 0, first time it's starting, right? Then it's creating a list, and second time it's running this this whole thing again, right? It's a new list altogether. Okay, with the same values though, but it's a new list. So hence when I change the third list ka fourth element to 4, only the third list ka fourth element is changed to 4, not the others. Okay, so fine. This is basically the idea behind all of this. Yeah, so underscore, it's nothing special, and underscore is a valid variable naming convention, right? I can write I, or I can write underscore I, or I can just write underscore also. This is basically used in a more like a for the sake of conveying the fact that I'm not using this index anywhere. For example, if I write I here and not use it anywhere, um, it's confusing because you'd say, okay, you are having a special value, a special name for it like I, but you're not using it anywhere. What's the point of naming it? So that's how we use this. That's how we keep this underscore with that. Okay, fine. So we'll meet tomorrow. We'll same 6 p.m. And we'll do a short rundown of the whole syllabus. Um, and if possible, come prepared. So if you have any questions, we can answer them on the fly. Okay. Okay, that's it for today. Thank you for joining.